History and Philosophy of Clojure. Clojure is a modern, dynamic, and functional dialect of the Lisp programming language on the Java platform. Created by Rich Hickey and released in 2007, Clojure emphasizes immutability, functional programming, and concurrency. Its design reflects a philosophy to be a general-purpose language that facilitates robust, practical, and scalable software development. This line of code is a simple demonstration of Clojure's syntax. The println function is used to output a string of text to the console. In this case, the traditional "Hello World" phrase is printed. While this does not delve into the deeper philosophies of Clojure, it represents the language's roots in Lisp, with its use of parentheses to denote function calls. The simplicity and expressiveness seen here are components of Clojure's philosophy to provide powerful language constructs in a concise manner. Functional Programming Paradigm. Functional programming, FP, is a programming paradigm that treats computation as the evaluation of mathematical functions and avoids changing state and mutable data. Clojure, being a functional language, encourages the use of immutable data structures and pure functions. A function is pure when it consistently returns the same result, given the same input, and it does not cause any side effects during execution. The code snippet above defines a pure function square that takes an argument x and returns its square. It then uses the map function, a cornerstone of functional programming, to apply square to each element of the list, 1, 2, 3, 4, 5. This is an example of using higher-order functions, which are functions that take other functions as arguments or return them as results. The code leverages immutability as the original list remains unchanged, while map returns a new list with squared values. REPL read eval print loop. REPL is an interactive programming environment that takes single user inputs, expressions, evaluates them, and returns the result to the user. It is a fundamental part of Lisp programming languages, including Clojure. The process is iterative and is particularly useful for experimenting with code and debugging. In this code snippet, we are asking the Clojure REPL to evaluate a simple arithmetic expression. The plus is a function for addition, and 2 and 3 are the arguments. The REPL reads this expression, evaluates it to calculate the sum, which is 5, and then prints the result out to the screen. Lastly, the REPL loops back to await the next input. Setting up a Clojure development environment. To begin developing in Clojure, we need to set up a development environment. This involves installing the Java Development Kit, JDK, Clojure itself, and optionally a build tool like Leiningen or Boot, and an integrated development environment, IDE, or a code editor with Clojure support. No code is required for this explanation, as we are discussing the steps involved in setting up the development environment, rather than writing Clojure code. The first step is to ensure you have Java installed, as Clojure runs on the Java Virtual Machine, JVM. The JDK can be downloaded from the official Oracle website or through open-source alternatives like OpenJDK. Then, install Clojure, which can be done through various means, such as downloading a standalone jar file or using a package manager. Finally, select and set up an editor or IDE. Popular choices include Emacs with Cider, IntelliJ with Cursive, or Visual Studio Code with Calva. For project management and dependency handling, tools like Leiningen or Boot are commonly used, and you can install them following their respective guides. Leiningen and Clojure Project Management. Leiningen is a build automation and project management tool for Clojure. It handles project's lifecycle from creating a new project, managing dependencies, running tests, to packaging and deployment. Here, we'll go through the process of creating a new Clojure project using Leiningen. This command creates a new Clojure project with the name myClojure app. It generates a directory structure following Leiningen's standard project layout, which includes necessary files such as project.clj for specifying project metadata and dependencies. Basic syntax and readability. Clojure's syntax is characteristically minimal and is built on a few primitive structures. In this example, we invoke the println function to output the string "Hello World" to the console. The parentheses denote a function call, while the quoted text is a string literal. This code demonstrates how to perform a basic output operation in Clojure. ClojureScript Introduction. ClojureScript is a variant of Clojure that compiles to JavaScript, thus it can run on browsers and other JavaScript environments. It leverages the rich functional programming tradition of Clojure while allowing developers to interact with JavaScript ecosystems. The code uses the println function, which is common in ClojureScript, to output a string to the console. It's a simple demonstration of ClojureScript syntax and the ability to perform I/O operations, much like Clojure, but the outcome is displayed in the JavaScript console of a web browser or a Node.js environment. Literals, numbers, strings, characters, booleans, nil. In Clojure, literals represent fixed values that are directly written into the code. These include numbers, strings, characters, booleans, and nil. Each has its own notation and use within the language. In the provided code snippet, a map named examples is defined using the def keyword. It associates keywords with their respective literals in Clojure. Number is paired with a numeric literal, the integer 42. String is paired with a string literal encapsulated in double quotes, Clojure. Character is associated with a character literal, prefixed with a backslash. Boolean is tied to the Boolean literal true. In Clojure, booleans can be true or false. Nil is connected to the nil literal, which represents the absence of a value, similar to null in other languages. Lists. In Clojure, a list is a collection of elements. Lists are defined by parentheses, and elements are whitespace separated. Lists are immutable, and they are implemented as linked lists, which means that operations at the start of the list are very efficient. Let's create a simple list and perform a few basic operations on it. This code snippet defines a list called myList with 5 elements, 1, 2, 3, 4, and 5. The def keyword is used to define a named variable. The first function returns the first element of the list, which is 1. The rest function returns a new list containing all the elements of myList except the first one, which in this case will be 2, 3, 4, 5. Remember that these operations do not modify the original list, but return new data structures instead. Vectors. In Clojure, vectors are a fundamental data structure that represent an ordered collection of values. Vectors are indexed by integers, allowing efficient access and update of elements at specific positions. They are immutable and have a fixed count of elements, but new vectors can be derived from existing ones with alterations. Let's explore how to create and manipulate vectors in Clojure. The code block demonstrates basic operations on a vector in Clojure. We define a vector named myVector with 5 integers. Using get, we access the second element. Indexing starts at 0, which returns the value 2. The conj function is used to add an element to the end of the vector, creating a new vector with the value 6 appended. Finally, assoc is used to update the element at the third index position, 2 since indexing starts at 0, to be 10, thus creating a new vector with the third element changed. Maps. In Clojure, maps are collections of key-value pairs often used to represent structured data. They are unordered, and the keys can be of any type, though they are commonly strings or keywords for convenience. A map can be created using the curly braces with alternating keys and values, or by using the hashMap function. The code provided shows 2 ways to create the same map in Clojure. The first line uses the literal syntax, where each keyword, e.g. a, is immediately followed by its corresponding value, e.g. 1. The second line creates a map using the hashMap function, which takes an even number of arguments, interpreting them as alternating keys and values. Sets. In Clojure, sets are collections of unique elements. They can be used to efficiently test for membership, remove duplicates from a collection, or perform set operations like union and intersection. Clojure sets are unordered and do not allow duplicates. A set is created using the hashSet function, or by placing a hash sign before a curly brace delimited list of elements. The code snippet demonstrates basic set operations in Clojure. Def mySet, hashSet1234, defines a new set named mySet, containing the numbers 1, 2, 3, and 4. Contains mySet3, checks if the element 3 is present in the set mySet. This will return true. Conj mySet5 adds the element 5 to the set mySet if it does not exist already. Disj mySet2 removes the element 2 from the set mySet if it is present. Keywords. In Clojure, keywords are tokens that begin with a colon, such as my key. They are often used as identifiers, and they can serve as keys in maps because they are unique and immutable. Keywords evaluate to themselves and are typically used for their identity rather than their absolute value. The code demonstrates the use of a keyword to look up a value in a map. Here, name is the keyword used as the key to retrieve the value Clojure from the accompanying map. Keywords act as a function that looks up their value in the map when placed before the map. Immutable data structures. In Clojure, all core data structures are immutable, meaning that once they are created, they cannot be changed. When we perform operations that seem to modify a data structure, we actually create a new data structure with the desired change. This has several advantages, including the simplification of concurrent programming and the prevention of accidental data mutation. Let's examine this concept through examples using lists and vectors. The code defines a list, my list, and a vector, my vector, both containing the elements 1, 2, and 3. The conj function is then used to add an element to each collection, creating new list and new vector. However, this does not change my list or my vector. Conj creates new versions of the data structures with the additional element. This shows how modification in Clojure means creating new data structures while the original remains unchanged, demonstrating immutability. Conditional logic, if when conned. The if statement is a fundamental control flow construct in Clojure, as in many other programming languages, allowing you to take different paths based on the truthiness of a condition. This code checks if x is greater than 10. If the condition, x10, is true, it evaluates and returns the first string, otherwise it returns the second string. The if construct evaluates the condition, then the true branch expression, and if the condition is false, the false branch expression. Loops loop recur. In Clojure, looping can be accomplished using the loop and recur special forms. Loop establishes a set of bindings much like let, but unlike let, loop creates a potential recursion point. Recur rebinds the variables and jumps back to the closest enclosing loop or function call, enabling efficient iteration. The code defines a loop with two variables, counter and sum. Counter starts at 0, and sum starts at 0 as well. Within the loop, there is a conditional that checks if counter is less than 10. If this condition is true, recur is called with the counter incremented by 1, and sum increased by the current value of counter. If the condition is false, when counter is not less than 10, the loop ends, and the current value of sum is returned. This loop effectively calculates the sum of the numbers 0 through 9. For comprehensions. In Clojure, for comprehensions are used to create a lazy sequence by applying an expression to each item in a collection or each combination of items across multiple collections. This feature is often used for iterating over data to produce new collections. Like a combination of map and filter, the for comprehension can both transform and filter items. In the provided code, a for comprehension is used to calculate the product of pairs of numbers within the range of 0 to 3. The x binding iterates over the first range, and for each value of x, the y binding iterates over the second range. The when keyword introduces a condition that filters the sequence, only allowing pairs whose product is less than 10 to be included. Each pair, along with their product, is collected into a tuple, xy, xy. The result is a lazy sequence of these tuples, filtered according to the specified condition. doSeek and doTimes. The doSeek macro is used in Clojure for side effects over a sequence. It is similar to for, but instead of creating a lazy sequence, it evaluates an expression for its side effects for each item in the sequence. In the code, doSeek iterates over the vector 1, 2, 3. The variable x takes on the value of each element, one by one. The println function is then called with x, which prints the numbers 1, 2, and 3 to the console, each on a new line. This is useful for operations like printing or writing to a file where you do not need to accumulate results. Case and switch. In Clojure, the case macro is used for doing conditional logic based on constant values. It is similar to the switch statement in other languages, but it can be more efficient, as it uses a hash table for constant time lookups when possible. The case form evaluates an expression and compares its result with a set of literals provided. In the code example, value is the expression being evaluated. If value is equal to 10, the case form will yield the string 10. If value is equal to 20, it yields 20, and if it is 30, it yields 30. If value does not match any of the provided literals, the default result is the string other. The case is useful when you have a known set of possible values for an expression and you wish to perform different actions based on those known values. Exception handling, try, catch, finally, throw. In Clojure, the try, catch, finally, and throw constructs are used to handle exceptions that occur during program execution. Try wraps a block of code that might throw an exception. Catch is used to specify handlers for different types of exceptions. Finally contains code that will execute regardless of whether an exception was thrown. And throw is used to explicitly raise an exception. The code demonstrates how to explicitly throw an exception within a try block using throw, handle it using catch, and execute cleanup code using finally. The throw form creates an exception with a message. If an exception occurs, the catch block catches the exception, allowing you to handle it, such as logging the error message. Regardless of whether an exception is thrown or caught, the finally block executes, often used for releasing resources or performing necessary cleanup actions. Defining functions, defn fn. In Clojure, functions are first-class citizens, which means they can be defined, passed around, and manipulated just like any other data type. The defn macro is a common way to define named functions, while fn creates anonymous functions. The defn example defines a function named greet that takes one argument name and returns a greeting string. The function is then called with the argument Alex. The fn example creates an anonymous function that takes one argument x and returns its square. This anonymous function is not assigned to a name, and thus can only be used in the context where it's defined or passed as a parameter to other functions. Anonymous functions. In Clojure, anonymous functions, also known as lambda functions, are functions that are not bound to an identifier. They are useful when you want to define a function for a one-time operation without the need to name it. You can create anonymous functions using the fn keyword or the shorthand syntax hashed. The provided code uses the map function to apply an anonymous function to each element of the vector 1, 2, 3, 4, 5. The anonymous function, specified by hasent2, doubles each element. The symbol sent represents the argument to the function. The result of the code is a sequence of the doubled values. Higher order functions. In Clojure, higher order functions are a powerful concept that allows functions to operate on and return other functions. They are a crucial part of functional programming, which enables abstraction and code reusability. Let's look at an example where a higher order function is used to create customized increment functions. The function makeIncrementer takes a number n and returns a new function. This new function takes a parameter x and increments it by n. We create two incrementer functions, inc_by_2 and inc_by_3, by calling makeIncrementer with 2 and 3 respectively. When we call inc_by_2 it returns 7, and inc_by_3 returns 8. This demonstrates how higher order functions can be used to generate specific functionality on the fly. Functionality. In Clojure, functionality refers to the number of arguments that a function can accept. Clojure supports defining multiple arities for a single function. This allows the function to perform different actions based on the number of arguments provided. The greet function defined above illustrates 3 arities. First arity takes no arguments and prints a default greeting. The second takes one argument, a name, and prints a personalized greeting. The third takes a name and a number times, and prints the personalized greeting multiple times. Calling greet with different numbers of arguments triggers the respective arity. Variadic functions. In Clojure, variadic functions can accept a variable number of arguments. These are useful when the number of arguments is not fixed and can vary with each call to the function. The syntax for variadic functions uses the rest parameter, preceded by an ampersand, to collect all remaining arguments into a sequence. In this example, sum is a variadic function that takes an arbitrary number of arguments. The an and args syntax creates a sequence called args that contains all the arguments passed to the function. Inside the function, reduce is used with the plus function to sum all the numbers in the args sequence. When the function is called with different numbers of arguments, args captures them all, and reduce applies the plus operation cumulatively to produce the sum. As shown, the function can be called with 3 arguments, 1, 2, 3, resulting in 6, or with 5 arguments, 4, 5, 6, 7, 8, resulting in 30. Recursion. Recursion in Clojure, as in many functional languages, is the concept of a function calling itself within its own definition. This is a powerful tool for solving problems that can naturally be broken down into smaller subproblems. Clojure has proper tail calls, which means that a function that calls itself in a tail position, as the last action it takes, will not grow the stack. This is important for recursion to be usable in practice. Let's look at a simple recursive function that calculates the factorial of a number. In this code, we define a function factorial that takes an argument n. If n is less than or equal to 1, it returns 1. This is our base case, and it's necessary to ensure that the recursion will eventually terminate. Otherwise, it multiplies n by the result of a recursive call to factorial with n decremented by 1 using dec. This recursive call breaks the problem into a smaller subproblem until we reach the base case. Without a proper base case, the function would call itself indefinitely, leading to a stack overflow error. Closures. In Clojure, a closure is a function that captures some of the local variables from its enclosing scope. When you define a function within another function, the inner function can access and use the local variables of the outer function, even after the outer function has finished executing. This concept is particularly useful for creating private data and factory functions. In the provided code, makeAdder is a higher-order function that takes an argument x and returns a new function. The returned function takes an argument y and adds it to x. The variable x is a local variable in makeAdder, but it is closed over by the returned function, thereby creating a closure. When makeAdder is called with 5, it returns a new function that adds 5 to its input. The function stored in add5 demonstrates this closure by adding 5 to its argument, so add510 yields 15. Macro basics. In Clojure, macros are powerful tools that allow you to manipulate code before it gets evaluated. They operate on the code's syntax tree, a form of metaprogramming. Macros are useful to extend the language and to create domain-specific languages within Clojure. The def macro expression defines a new macro named hello, which takes one argument, name. The backtick is syntax quotation. It returns the form that follows it without evaluating it, whereas chash is unquote. It evaluates the form in the context where the macro is called. The macro, when called with hello world, will expand to println hello world, and then evaluate it, printing hello world. Namespace management NSUs require refer. Namespaces are a way to organize and manage different parts of your code. In Clojure, namespaces are used to group related functions and variables. This helps prevent naming conflicts between different parts of a system. The ens macro is most commonly used to declare a namespace. Additionally, use, require, and refer are mechanisms to include code from one namespace into another. In this example, ens declares a new namespace named my.namespace. Inside the parentheses, we have directives that manage dependencies. Require Clojure.string as str includes the Clojure.string namespace and gives it an alias str. This way we can call its functions like so. Str use Clojure.set brings in all the public symbols from Clojure.set, so you can use them without any namespace prefix. Refer Clojure exclude map prevents the map function from Clojure's core namespace from being used in this namespace, which is useful if you wish to define your own map function without conflict. Creating and using libraries. In Clojure, a library is a collection of related functionality encapsulated in one or more namespaces. To create a library, we'll define a new namespace, then create the functions and definitions we want to provide. Finally, we can make our library available to others by using tools like LineEngine to package and distribute it. This code snippet is the creation of a simple Clojure library. The ns macro is used to define a new namespace called mylibrary.core. We then define a function greet that takes a single argument name and returns a greeting message as a string. This function serves as part of the library's API that can be used by other programs. Dependency management. In Clojure, dependency management is handled by tools that manage external libraries your project requires. A commonly used tool is LineEngine. In a LineEngine project, dependencies are listed in the project.clj file under the dependencies key, where each dependency is a vector containing the library name and its version. The code defines a LineEngine project configuration where the myClojure project has two dependencies. The first dependency is the Clojure core library at version 1.10.1, which is essential for every Clojure project. The second dependency is tools.logging at version 1.1.0, which provides logging facilities. When you run LineEngine commands like linedeps, it reads this configuration and fetches the specified versions of the libraries from remote repositories and stores them in your local system so that your project can use them. Common libraries and tools. LineEngine is the de facto build automation and dependency management tool for Clojure. It handles project creation, dependency resolution, running tests, packaging, and many other tasks. Below is an example showing how to specify dependencies in a LineEngine project file, known as project.clj. The code block represents the project.clj file of a Clojure project using LineEngine. It includes project metadata, name, version, description, etc., and a list of dependencies with their versions. Here, org.clojure/Clojure is the Clojure language itself, and clj-time is a popular library for date and time manipulation. LineEngine would fetch these dependencies from Clojure's or Maven central repositories when setting up the project. Interop with Java. Clojure runs on the Java virtual machine and can interoperate with Java code. You can use existing Java libraries directly from Clojure. Let's see how to call a method of a Java object in Clojure. The above code snippet demonstrates how to call the toUpperCase method of a Java string object from within Clojure. The dot prefix is the syntax Clojure uses to invoke instance methods on Java objects. The result of the expression will be the string Clojure, immutable versus mutable state. In Clojure, state can be categorized into two types, immutable and mutable. Immutable state refers to data that cannot be changed once it is created, while mutable state refers to data that can be changed. Clojure strongly favors immutable state and provides several constructs to work with it efficiently. Below is a simple demonstration of how immutable state works in Clojure using a vector, which is an immutable data structure. In the code, myVector is a vector, an immutable data structure containing 3 integers. The conj function stands for conjoin and is used to return a new vector with the additional item 4 added to the end. However, this does not change myVector. Instead, it creates a new vector. This behavior exemplifies the concept of immutable state, where the original state does not get altered. In Clojure, most of the core data structures, vectors, lists, maps, and sets, are immutable. Atoms. In Clojure, atoms provide a way to manage shared, mutable state that ensures changes occur in a thread-safe, atomic fashion. They are ideal for scenarios where you want to update a value without locking and without worrying about other threads seeing intermediate states. An atom is updated with the swap function, which applies a function to the atom's current value, along with any additional args. Here, an atom named counter is created, initially set to 0. The swap function is first used to increment the current value of the atom using inc. After another swap, the value is updated by adding 3 to it. @counter is used to dereference the atom and retrieve its current value. The result of this sequence will be that counter holds the value 4. Refs. In Clojure, refs are a way to manage state that needs to coordinate changes from multiple threads. Refs provide synchronous, coordinated, and transactional access to mutable shared states, somewhat like transactions in a database. In this code snippet, dosync is used to create a transactional context within which refset, alter, and commute functions are used to update the state of myref, other ref, and yet another ref, respectively. Refset sets the value of myref to 42, alter applies inc function to other ref to increment its value, and commute applies SHA2 to yet another ref to double its value. Agents. Agents in Clojure are a means of managing state in a concurrent, asynchronous manner. Actions are functions that are asynchronously applied to an agent, which will then hold the new state after the function has been applied. Unlike refs and atoms, agents support off-the-main thread execution and don't block the caller. In this code, we define an agent called counter that initially holds the value 0. We then send two actions to the agent. First, we increment the value with inc, then we add 3 to the current value. The send function queues the actions to be processed by the agent in a separate thread. Calling @counter dereferences the agent, giving us the current value after actions are applied. If actions are in process, dereferencing an agent will block until all actions sent prior to the dereferencing are completed, ensuring a consistent view of the state. var usage. In Clojure, a var is used to refer to a location that holds a value and can be dynamically rebound. A var is created using def and can be used to ensure thread local values with binding. Below is an example code showing how to define and manipulate a var. This code defines a dynamic var named tar_my_var with an initial value of 10. The update var function then uses binding to rebind my_var to a new value of 20, but only within the scope of the binding form. When nar_my_var is printed before and after calling update var, it shows the original value 10, because the rebinding was only effective within the update var function. Software Transactional Memory (STM). In Clojure, Software Transactional Memory (STM) allows safe concurrent access to shared mutable state. STM works by grouping code into atomic transactions, which can safely retry or abort if they conflict with other transactions. Clojure provides special reference types such as ref that are designed to be used within these transactions. In this snippet, dosync begins a transaction that modifies two refs, ensuring atomicity and isolation. Refset sets my_ref to 42, and alter applies inc to increment other ref. If a conflict occurs during execution, such as another thread modifying other ref, the transaction will automatically retry until it can complete successfully without interference. Concurrency constructs. In Clojure, an atom is a reference type that manages mutable state in a thread-safe way. Atoms are changed with the swap function, which atomically sets the value of the atom to the result of applying a function to its current value. In this code snippet, we define an atom counter with an initial value of 0. Then we use swap to increment the counter atomically. The inc function is applied to the current value of counter, 0, resulting in 1. Finally, we dereference counter using the symbol to fetch its current value, which will be 1. Parallelism pmap futures. In Clojure, parallelism can be achieved using various constructs. Pmap is used for parallel processing of sequences, and futures are used for asynchronous computation. Using pmap ensures that the CPU-bound tasks utilize multiple cores. Futures, on the other hand, are useful for performing a task in the background and retrieving the result later. This code defines an expensive computation function, then applies it to a vector of numbers using both pmap and future. The pmap function automatically distributes the computation across multiple threads. The results pmap will be a lazy sequence. Evaluation happens in parallel as the results are consumed. Meanwhile, future starts a background task for the entire computation. The results future holds a future object that can be dereferenced to obtain the result once computation is complete. Seek abstraction. In Clojure, the seek abstraction is a logical list which can be used to access the elements of a collection sequentially. It provides a uniform way to process different types of collections, such as lists, vectors, maps, and sets. The abstraction is based on 3 core operations. First, to return the first element, rest to return everything except the first element, and cons to add an element to the beginning of the seek. In this code, the first function returns the first element of the vector, 1, 2, 3, which is 1. The rest function returns a seek of all elements except the first, which gives us 2, 3. The cons function adds the element 0 to the beginning of the vector, resulting in the seek, row 1, 2, 3. Even though we used a vector, these functions work similarly on other collections due to the seek abstraction. Lazy sequences. In Clojure, a lazy sequence is a sequence whose elements are computed on demand and cached. This allows for the creation of potentially infinite sequences while using memory efficiently. When a value in the sequence is needed, Clojure evaluates only enough of the sequence to produce the value. This example demonstrates a lazy sequence in action. The range function creates a lazy sequence of natural numbers starting from 0. The map function incrementally applies increment function to each number, also lazily. Finally, take is used to retrieve the first 10 incremented values. Because all of these functions return lazy sequences, the computation only occurs when we realize the first 10 values, rather than calculating all increments up front. Common sequence functions. In Clojure, sequences are abstract descriptions of collections. This abstraction allows for powerful and concise operations on any collection that can provide a sequence interface. Common sequence functions operate on these abstractions to filter, transform, and aggregate data with ease. Let's explore some of these functions. The map function applies increment to each element in the vector, resulting in 2, 3, 4. Filter creates a new sequence of even numbers, producing 2, 4. Reduce applies plus to combine all elements into a single sum, resulting in 10. Take retrieves the first two elements of the sequence, giving us 1, 2. Drop removes the first two elements, yielding 3, 4. Each function transforms the sequence in a specified manner, demonstrating the elegance and utility of sequence functions in Clojure. Sequence transformations. In Clojure, sequences can be transformed using various functions that take a sequence as input and produce a new sequence as output, without altering the original sequence. This concept is central to functional programming, where data remains immutable. Let's explore some common sequence transformation functions like map, filter, reduce, and take. The map function applies a given function, in this case which increments a number by 1 to each element in the sequence, producing a new sequence of incremented values. Filter selects elements that satisfy a predicate function, odd in the example, which selects odd numbers. Reduce folds a sequence into a single value by applying a function, here plus for addition, between elements. Take returns a new sequence containing the first n elements, 3 in this case, from the original sequence. Reducers. In Clojure, reducers are a way of processing collections in a more efficient, composable, and parallelizable manner compared to the standard collection functions. A reducer is a function that takes a reducing function and a collection and applies the reducing function sequentially to the elements of the collection. The reducing function itself takes two arguments, an accumulator and the current item, and it returns a new accumulator. This is particularly useful for large datasets or performance-critical code, where you can benefit from parallel execution using clojure.core.reducers/fold. The provided code demonstrates two uses of reducers. The first let binding calculates the sum of a collection of numbers using r/reduce, which is similar to Clojure's built-in reduce, but designed for use with the reducers framework. The second let binding showcases how reducers can be composed. It filters the collection to only even numbers using r-filter, then doubles each number using r-map, and finally sums the processed numbers using r-fold for potential parallelism. Fold uses a divide-and-conquer strategy that can be executed in parallel, unlike reduce, which processes items sequentially. Transducers. Transducers are composable algorithmic transformations. They are independent of the context of their input and output sources, and can be used to process streams of data. Unlike map or filter, which work on collections, transducers are functions that take a reducing function as an argument and return a new reducing function that accumulates results according to some transformation. In the provided code, XF is a composed transducer that first filters odd numbers and then increments each. The transduce function takes this transducer, a reducing function plus an initial value 0, and a range of numbers from 0 to 9. It applies the transducer to the range and combines the results using the plus function, resulting in the sum of incremented odd numbers from the range. Sequence generators range, iterate, repeat. The range function is used to create a lazy sequence of numbers. It can take 0, 1, 2, or 3 arguments, defining the start, inclusive, end, exclusive, and step values respectively. Without arguments, it starts from 0 and increments by 1 indefinitely. In the provided code, range 0, 10, 2 generates a sequence starting at 0, increases by 2 each step, and stops before reaching 10. This results in a sequence of even numbers from 0 to 8. Understanding macros. In Clojure, macros are powerful tools that allow you to write code that manipulates code. They enable metaprogramming, which is the act of writing programs that produce or modify other programs. Macros operate on the syntactic structure of the code, which means they can transform code before it is evaluated. In the given code sample, we define a macro called deflog, which creates a function that, in addition to executing its body, prints a log message every time it's called. The macro uses syntax quoting, unquoting, and unquote splicing, to construct the new function definition. The function myfunc is defined using this macro, and when called with arguments 3 and 5, it will print function myfunc called with arguments and return the sum of the arguments. Defining macros. In Clojure, macros are a powerful tool that allow programmers to introduce new syntactic constructs in a clean way. Unlike functions, macros perform transformations on the code itself at compile time, allowing for more abstract and expressive code. Defining a macro involves using the def macro keyword, followed by the macro name and a parameter list, then the body of the macro, which specifies how the input forms should be transformed into the output code. This is an example of a simple macro that defines when not, which is a conditional construct that only executes the body expression if the condition is false. The macro uses syntax quoting, backtick, and unquote to build the resulting structure. Syntax quoting allows us to write the template of the code that will replace the macro call, and unquote is used to incorporate the actual arguments. Operator is used to splice a sequence of expressions into the code. When not takes any condition conned and executes body only when conned is not true. Macro expansion. Macro expansion is the process where macro expressions are transformed into lower-level code before being evaluated. This occurs during the compilation phase, allowing developers to manipulate code structure and synthesize new code programmatically. In the provided code, def macro is used to define a new macro named debuglog. It takes one argument, MSG, and produces a code template that expands to a println function call. The syntax quote, backtick, creates a template, and unquote tilde is used to include the value of MSG within it. When debuglog. Reader macros. Reader macros in Clojure are not to be confused with standard macros. A reader macro is a character or a sequence of characters that tells the reader how to interpret the following characters. Common reader macros in Clojure include quote, syntax quote, unquote, and unquote splicing, In this code, the single quote is a reader macro that is shorthand for quote. It prevents the evaluation of the symbol x in the function definition and hello in the function call. Instead, x is treated as a symbol and hello as a quoted list. Macro patterns. In Clojure, macros are a powerful tool to abstract repetitive code patterns and enable syntactic extensions. They work by manipulating the abstract syntax tree, AST, before the code gets compiled. Here, we explore some common macro patterns that are often used in Clojure development. The provided with open file macro illustrates the resource management pattern. It automates the process of opening a resource, in this case, a file, and ensures that it gets closed after completing the body. In the code, binding is the binding vector that holds the file and variable name. Body is the body of the macro to be executed with the file open. Streamshack is an autogensim variable to prevent naming collisions. The try block is to ensure the file gets closed even if an error occurs in body. The macro expands into a let binding with try finally for resource management. Compiler directives. In Clojure, compiler directives are special forms that provide instructions to the Clojure compiler. These forms can control various aspects of the compilation process. A common directive is the use of metadata attached to symbols or expressions that can inform the compiler about type hints, deprecation, and other attributes that may optimize the generated bytecode. The code defines a function fastAdd that takes two arguments, a and b. The long metadata before both the function name and the parameters is a type hint that indicates to the Clojure compiler that both the input arguments and the return value should be treated as primitive longs. This enables the JVM to perform optimizations it couldn't do if Clojure used its default numeric type hierarchy, potentially resulting in faster execution time. Macro metaprogramming techniques. Macros in Clojure are used to extend the language's syntax and provide abstractions by operating on code as data, homoiconicity. They execute at compile time to manipulate and generate code. The macro when not takes a predicate and an expression. It generates an if expression that will execute the given expression only if the predicate is false. The tilde is used for unquoting in the syntax quoted list, generating code at compile time. In Clojure, macros are a powerful tool that allow us to generate and manipulate code at compile time. By generating code, we can create abstractions, reduce repetition, and build domain-specific languages, DSLs. A macro is a function that takes code as its input and produces new code that is then compiled and executed. This example defines a simple macro when not that acts as the inverse of Clojure's built-in when macro. When not is used, it takes a condition and a body of expressions. During compilation, if the condition is not met, the body is expanded into a when form with the negated condition. This allows code to be conditionally included in the program's execution based on the provided condition. Upon macro expansion at compile time, the when not example would produce code equivalent to when not pos x, println x is not positive in x. Calling Java from Clojure. Clojure runs on the Java Virtual Machine, JVM, and can directly call Java code, leveraging Java's rich set of libraries. The syntax for interop is concise and allows for seamless integration of Java functionality within Clojure's codebase. The code snippet involves calling the substring method on a Java string. The syntax begins with a dot, followed by the method name, and then the object and arguments. Here, Clojure interop is the object, and 8 is the argument representing the starting index. It returns the substring from the 8th character to the end, which will be interop. Working with Java collections. Clojure provides seamless interoperability with Java, allowing Clojure programs to use Java collections directly. Clojure also provides a set of functions to work with Java collections as if they were native Clojure collections. The code snippet demonstrates how to create and use Java collections from Clojure. We import the ArrayList and HashSet classes from java.util package. In the demo Java collections function, we initialize an ArrayList instance, AL, and a HashSet instance, HS. Using the .add method, we add the strings Clojure to the ArrayList and interop to the HashSet. We then convert these Java collections to Clojure sequences using CQ and return them in a map. After invoking demo Java collections, you will get a map with the sequences of the added elements. Java exceptions handling. In Clojure, Java exceptions can be handled using the try, catch, finally constructs, similar to Java. Clojure code that calls Java methods may need to handle exceptions those methods can throw. Here's how you might catch and handle a file not found exception in Clojure. The try block contains the code that may cause an exception. If a file not found exception occurs, control moves to the catch block where the exception is bound to E. Inside catch, we print the exceptions message. The finally block is optional and contains code that will execute regardless of whether an exception occurred or not, often for resource cleanup. It is important to match the exception class correctly. If the caught exception type does not match the thrown exception, it will not be handled and will propagate up the call stack. Using Java libraries. Clojure runs on the Java Virtual Machine, JVM, and seamlessly interoperates with Java. This enables Clojure programs to utilize Java libraries, giving access to a vast ecosystem of existing Java code. Interoperability is straightforward thanks to a set of special forms and functions provided by Clojure for this purpose. The given code demonstrates how to use Java libraries in Clojure. The import statement makes the date class from the java.util package available. The defn creates a Clojure function called getCurrentDate that, when called, creates a new instance of the Java date class using date, and converts it to a string using the str function. This will provide the current date and time according to the system's locale and time zone. Creating Java classes in Clojure. In Clojure, It is possible to define Java classes using the gen class macro. This is often done when you need to integrate with Java code that expects certain classes, or when crafting libraries for use in Java. Here's a simple example of how to define and use a basic Java class in Clojure. The gen class directive in the namespace ns form specifies that we want to generate a Java class with the name example.hello. We declare a method greet with an empty argument list that returns a string. The corresponding Clojure function -greet is defined with the prefix, which indicates a Java instance method, and takes this as its argument, returning a string greeting. When this Clojure code is compiled, it will generate a Java class file named example.hello.class that can be used like any other Java class. Interfaces and protocols. In Clojure, the ability to interact with Java is a fundamental feature since Clojure runs on the Java Virtual Machine, JVM. Two key concepts for interacting with Java code are interfaces and protocols. Interfaces define a contract that can be implemented by any class, whereas protocols provide a similar mechanism within Clojure to define a set of functions that can be implemented for different data types. In the provided code, we define a protocol P with two methods, foo and bar. A protocol is similar to a Java interface, but is used within Clojure to specify a set of functions. We then define a record R that implements the protocol P, providing concrete implementations for foo and bar. The let block creates an instance of R and demonstrates invoking the foo and bar methods on that instance. This shows how protocols can be used to define a set of methods, and how different data types can implement these methods to provide specific functionality. REPL-driven development. REPL-driven development is a programming approach specific to Clojure and other Lisp-like languages. The REPL, read-eval-print loop, is an interactive programming environment that takes single expressions, evaluates them, and returns the result. This process encourages experimentation and provides immediate feedback, making it a powerful tool for development and debugging. In this code, greet is a function that takes a single argument name and returns a greeting string. The function is then immediately called with the argument world to demonstrate how feedback is obtained in a REPL. In practice, you would send this code to the REPL, it would be compiled on the fly, and you would see the output, hello world, right away. This quick feedback loop is integral to REPL-driven development, allowing you to modify and re-evaluate code with ease. Debugging and error handling. Debugging in Clojure often involves identifying the cause of an exception or incorrect behavior in the code. Clojure provides a REPL, which can be used for experimenting and testing code snippets. Additionally, Clojure stack traces can be quite verbose, so knowing how to read them is crucial for debugging. Error handling is commonly done using the try-catch mechanism, similar to Java. The following code shows a simple example of error handling. In the provided code, we are attempting to divide 1 by 0, which will naturally throw an arithmetic exception. The try block wraps the dangerous operation, while the catch block is ready to handle this specific type of exception. When the exception occurs, instead of crashing the program, the catch block catches it and prints out a message to notify the user of the issue. Note that try-catch can also handle multiple different exceptions and can include a finally block to execute code, regardless of whether an exception occurred. Testing unit tests property-based tests. In Clojure, testing is an essential part of the development process. It helps ensure that your code works as expected. Clojure provides a built-in library called Clojure.test for unit testing, which allows developers to write test cases to check the correctness of individual units of code. This code snippet demonstrates a basic unit test in Clojure using the Clojure.test namespace. The ends declaration sets up the namespace for the test. Deftest is used to define a new test called a test, and testing provides a context for what the test is about. The is macro asserts that the expression within it, in this case, +2 equals 4, evaluates to true. Profiling and performance optimization. In Clojure, profiling is the process of measuring the space, memory, and time complexity of code. Performance optimization aims to make the code more efficient by identifying bottlenecks and eliminating them. Clojure provides several tools for profiling, like Criterion for benchmarking and your kit or visual VM for more detailed profiling. In the code snippet, we define a function computeFib to calculate the nth Fibonacci number. Then, we use the bench function from the criterion library to benchmark this function with the input 20. The bench function will execute the computeFib function multiple times and provide statistical information about its execution time, allowing us to identify performance bottlenecks. Continuous integration and deployment. Continuous integration, CI, and continuous deployment, CD, are practices in software development that enable teams to deliver code changes more frequently and reliably. In a Clojure project, you can set up CI/CD by using a combination of version control systems, build tools such as Leiningen or Boot, and CI/CD platforms like Jenkins, CircleCI, or GitHub Actions. The provided code is a Jenkins pipeline script. It defines a series of steps to check out the code, run tests with Leiningen, and deploy the application when the master branch is updated. Each stage represents a part of the CI/CD process. The test stage executes the line test command to run the Clojure project's test suite. If the tests pass and the code is on the master branch, the deploy stage executes the line deploy command to deploy the application. This script exemplifies how CI/CD can automate the testing and deployment of a Clojure application. Code formatting and linting. In Clojure, as in other programming languages, maintaining a consistent code style and following best practices is important for readability and maintainability. Two tools that can assist in this task are formatters and linters. A formatter will automatically lay out code according to a set of style rules, and a linter will analyze code to flag programming errors, bugs, stylistic errors, and suspicious constructs. In the provided code snippet, the namespace is defined, followed by a function greet that takes a single argument, name. It returns a greeting string. The code is formatted with proper indentation to enhance readability. Each nested expression is indented 2 spaces relative to its parent. Correct formatting would be ensured by a formatter tool. Additionally, a linter could check for potential issues such as unused variables or functions, adhering to idiomatic practices like using kebab case for function and variable names, ensuring proper variable scope, and more. Editors and IDEs support. The development experience in Clojure can be significantly enhanced through the use of dedicated editors and integrated development environments, IDEs. Here we will look at an example of setting up a Clojure environment in the popular editor, Emacs, using the Cider package. In this Emacs Lisp code snippet, we add the melpay repository to the list of package archives, which allows us to install packages that are not part of the default Emacs package set. The package install command is then used to install Cider, which is a Clojure IDE and REPL for Emacs, enhancing it with powerful Clojure-specific features. Ring and HTTP handling. In Clojure web development, Ring is a core library that provides abstractions for handling HTTP requests and responses. Ring models an HTTP server as a function that takes a request map and returns a response map. Middleware, which can modify or manipulate these maps, allows for flexible and composable handling of HTTP interactions. The code snippet demonstrates a simple HTTP server built with Ring and Jetty. First, we require the Jetty adapter from the Ring library. We then define a handler function, which takes a request map and returns a response map representing an HTTP 200 status, with a plain text content type and a body of Hello World. Finally, we use Jetty's run Jetty to start the Jetty server on port 3000, passing our handler function to manage incoming HTTP requests. Web frameworks, Clojure WriteIt. Clojure is a small routing library for Ring that allows the definition of web routes in a concise and expressive way. It helps to map HTTP requests to functions that process and generate responses. The code defines a simple Clojure application with 2 routes. The defroutes macro is used to create a routing table. The first route matches the route URL and returns a welcome message. The second route demonstrates parameter extraction, responding to paths like /hello Alice with a personalized greeting. Wrap defaults applies common middleware to the app routes. Finally, the app is started on port 3000 using the Ring Jetty adapter. Middleware. In the context of web development in Clojure, middleware refers to functions that sit between the web server and the application. They can process the incoming request, the outgoing response, or both, potentially altering them or triggering side effects. Middleware functions wrap around the handler, which is the function that processes the request and produces a response. They are a powerful way to abstract common functionality, such as logging, authentication, and session management. The provided code defines a simple middleware function, REPL, which takes a handler function as an argument and returns a new function. This new function prints a message to the console every time a request is received, and then calls the original handler. When REPL is applied to some handler, it returns a new handler, app handler, that includes the logging behavior. API Development REST GraphQL. REST, which stands for Representational State Transfer, is a set of principles for designing web services that expose a predefined set of stateless operations. RESTful services use HTTP requests to perform CRUD, create, read, update, delete operations on data. Clojure, with libraries like Ring and Compojure, is well suited for creating RESTful APIs. In the provided Clojure code, we define a namespace api.handler and require the necessary libraries. The defrotes macro creates routes for handling HTTP GET and POST requests at the items endpoint. GET requests return a list of items, while POST requests signify item creation. The app definition handles all non-mapped routes and returns not found. Front-end integration. In Clojure web development, front-end integration often refers to the interaction between Clojure-based back-end systems and front-end technologies. The front-end can be a ClojureScript application or a web page using JavaScript frameworks. One common approach is to use Reagent, a ClojureScript interface to React, for building the user interface. Here, a ClojureScript function homepage is defined using Reagent to create a React component. The vector syntax, provided by Hiccup, a Clojure library, is used to represent the HTML structure of the page. When this code is compiled, it translates into React.createElement calls to render the given HTML structure. WebSockets. WebSockets provide a way to establish a persistent, low-latency communication channel between a client and a server. They enable real-time data transfer, making them ideal for chat applications, live notifications, and interactive games. In Clojure, we can use libraries like Sente to handle WebSockets. The code defines a Clojure namespace that requires the Sente library, setting up the basic infrastructure for handling WebSockets. It defines an atom to store state and a Sente config, specifying how to extract a user ID from a request. MakeChannelSocket is called with an HTTP KIT server adapter to create the necessary functions for sending messages, send, tracking connected users, connected UIDs, and handling AJAX post requests, AJAX post. These can be used to establish and manage WebSocket communications. Web security. Web security in Clojure involves safeguarding applications against potential threats. This typically involves setting up HTTPS, securing against cross-site request forgery, CSRF, and sanitizing inputs to prevent SQL injection and cross-site scripting, XSS. Here we'll focus on implementing CSRF protection using the Ring middleware. The code snippet demonstrates the integration of CSRF protection within a Clojure web application using the ring.middleware.anti-forgery namespace. The wrap anti-forgery function is a middleware that adds anti-forgery measures, such as a token validation process, to your handler. When included in your app's middleware stack, it ensures that only forms with valid anti-forgery tokens are accepted by the server, blocking CSRF attacks. Working with databases. In Clojure, working with databases often involves using a library to facilitate database interactions. One standard library for SQL databases is clojure.java.jdbc, which provides a simple and idiomatic way to execute SQL queries. Let's look at an example of how to connect to a database and retrieve data from a table using this library. In this code snippet, we require the clojure.java.jdbc library and define a DB-spec map that holds our database connection details, such as the type of database we're connecting to, PostgreSQL, the database location, localhost at port 5432, and the credentials, user and password. Using the JDBC query function, we pass our DB-spec and a parameterized SQL query to select all columns from the users table where the ID is 1. The JDBC/query function returns the query result as a sequence of maps, with each map representing a row in the result set. Datomic and data modeling. Datomic is a database that centers around immutable data and provides rich features like time travel queries. Unlike traditional databases, Datomic treats all data as facts that accumulate over time, allowing us to gain insights into the state of the database at any point in history. In Datomic, data is modeled through a combination of attributes, entities, and relationships between entities. Let's look at a simple code example that demonstrates how to define a new database schema in Datomic. The code defines a Datomic schema with 3 attributes for a hypothetical person entity. The first attribute, person's name, expects a string and has a cardinality of 1, meaning a person has only one name. The second attribute, person's age, is a long integer with a cardinality of 1. The third attribute, person's friends, is a reference to other person entities, which indicates relationships and has many cardinalities, suggesting that a person can have multiple friends. Defining a schema like this allows Datomic to understand and store data about persons efficiently, ensuring both data integrity and the powerful querying capabilities that Datomic provides. SQL databases and JDBC. Interacting with SQL databases in Clojure typically involves using JDBC, Java Database Connectivity, which is a Java API for connecting to relational databases. Clojure, being a hosted language on the JVM, can leverage the JDBC API through Java interoperability. This allows Clojure to execute SQL queries, retrieve results, and handle transactions. In this code, we're requiring the clojure.java.jdbc library, which provides functions to interact with databases. The DB spec map defines the database connection details. The JDBC query function is then used to run a SQL query on the database specified by DB spec. The query will select all fields from the users table where the ID is 1. The @ is a placeholder for parameters in the SQL query, and 1 is passed as the parameter to replace the placeholder in the query. NoSQL databases. Cassandra MongoDB. NoSQL databases are designed to store, retrieve, and manage large volumes of unstructured, semi-structured, or structured data. Cassandra and MongoDB are popular NoSQL databases. Cassandra is designed for high availability with no single point of failure, while MongoDB is a document-oriented database that allows for flexibility in the data model and easy scalability. While Clojure is not traditionally used for managing database infrastructure, it can interact with NoSQL databases through client libraries. There is no specific Clojure code block provided here, as interacting with Cassandra or MongoDB would require setting up the respective databases and using client libraries such as Cassandra Driver for Cassandra or MongoCLJ for MongoDB. Typically, you would perform operations like connecting to the database, creating records, reading records, updating records, and deleting records using the functions provided by these libraries. ORM and Hibernate. Object Relational Mapping, ORM, is a programming technique for converting data between incompatible systems using object-oriented programming languages. Hibernate is a popular ORM framework for Java that enables developers to write applications whose data outlives the application process, mapping Java classes to database tables. Clojure, being hosted on the JVM, can also leverage Hibernate through interop. The code snippet shows how to set up a Hibernate session factory in Clojure. A Hibernate configuration object is created and configured with hibernate.cfg.xml file. The session factory is then built, which will manage the database sessions and serve as the main runtime interface between a Java application and Hibernate. Database migrations. In the context of data persistence, database migrations refer to the management of incremental, reversible changes and version control to a database's schema. Migrations allow you to evolve your database schema over time in a consistent and easy-to-track manner. They can be applied to create tables, alter existing tables, add indexes, and more, without requiring you to manually write SQL for every change. Typically, database migration includes a set of files that describe how to move from one database version to another. Each file contains instructions for making changes to the database schema, including creating new tables, altering existing tables, and more. Using a migration tool, these migrations can be applied or rolled back as needed. Clojure doesn't have built-in support for database migrations, but libraries such as Migratus or Flyway can be integrated to manage the process. These tools store the state of applied migrations, and ensure changes are made in a controlled way. Performance tuning and JVM profiling. Performance tuning in Clojure involves optimizing code to run faster or use fewer resources. JVM profiling is a technique to monitor the performance of Java Virtual Machine (JVM) applications, including those written in Clojure. It helps in identifying bottlenecks, memory leaks, and CPU-intensive operations. The provided code demonstrates a more performant version of calculating Fibonacci numbers by using the loop and recur constructs to efficiently iterate without consuming stack space. The time macro is used to measure the execution time, providing insight into the performance of the function. Profiling this using JVM tools can further reveal if there are any hidden performance issues. Distributed systems. In the context of Clojure and distributed systems, we can leverage libraries like Onyx Platform or Hazelcast to coordinate tasks across different nodes in a cluster. Onyx is a powerful distributed computation system that allows you to write code once and run it at scale across a cluster of machines. Here, we'll look at an example of using Onyx to define a simple job that counts words in a distributed manner. The code snippet is a job descriptor for Onyx. It consists of 3 segments: input, task, and output. Each segment contains a component that processes or transfers data through channels using core.async. The input segment uses a core.async channel to intake data. The word count task then computes the word frequencies using Clojure's frequencies function. Finally, the output segment sends the output to another core.async channel. A job is submitted with Onyx/submit job, specifying the job structure, job, flow between tasks, flow, and configuration, job config. This example illustrates a simple distributed computation where work could be parallelized across multiple peers. Message queues and event streaming. In Clojure, interaction with message queues and event streaming can be managed through various libraries. For illustration, we'll use the Amazon Simple Queue Service (SQS) as an example of a message queue. We'll show how to use the Amazonica Clojure library to interact with SQS. The code uses the Amazonica library to send and receive messages to and from an SQS queue. First, it requires the SQS namespace. After defining the queue URL, it sends a message using SQS/sendMessage. Then, it attempts to receive messages with SQS/receiveMessage. If there is a message, it prints out the message body and then deletes the message from the queue using SQS/deleteMessage to prevent it from being processed again. This is a common pattern when dealing with message queues, where consumers poll the queue, process messages, and remove them from the queue to acknowledge successful processing. Clojure in the cloud. Deploying Clojure applications in the cloud usually involves packaging your app as a standalone jar or Docker container and utilizing cloud-native services. A common pattern is to create a RESTful API with Clojure and deploy it on a cloud platform. The provided code is a Clojure snippet that starts a web server using the runJetty function from the ringJetty adapter library. It retrieves the port number from an environment variable, a practice that aligns with cloud deployment configurations where the port is often assigned by the cloud environment. Upon executing, a server instance is created and starts listening for incoming HTTP requests on the specified port. Clojure and machine learning. Clojure, being a functional language that runs on the JVM, can interoperate with Java libraries. For machine learning tasks, we can leverage libraries like Weka or Deep Learning 4J. Let's consider a simple example using the Neanderthal library, a Clojure wrapper for efficient numerical computation, which is important in machine learning. In this example, we require the Neanderthal library for its efficient numerical operations. We define a function, Euclidean distance, that calculates the Euclidean distance between 2 vectors, which is a basic operation in many machine learning algorithms. Here, dv is a function from Neanderthal to create dense vectors. The example concludes by creating 2 dense vectors, vector 1 and vector 2, and then computing their Euclidean distance using our defined function. Creating DSLs in Clojure. Domain-specific languages, DSLs, are small languages tailored to a specific domain. Clojure, with its macro system and higher-order functions, is well suited for creating DSLs. Let's create a simple DSL for mathematical operations that showcases how easy it is to extend Clojure with custom syntax. In this code snippet, we define a macro mathop that takes an operator and a variable number of arguments. The macro expands into a reduce call that applies the operator to the arguments. Using this DSL, we can perform math operations with a syntax that is closer to mathematical notation. The first example adds the numbers 1, 2, 3, and 4, resulting in 10. The second example multiplies the numbers 2, 3, and 4, resulting in 24.